Picture this. It is early morning, the sun barely lifting the darkness. An older farmer in rural Japan bends down, dissolves a small packet of white powder into a bucket of water, and quietly sprinkles it over a patch of straw-covered earth. No heavy machinery, no expensive chemicals, no expert consultants, just the powder, water, and the quiet of the dawn. When he returns the next morning, the ground is transformed. Beneath the straw, hundreds of earthworms are stirring. The soil is rich and loose, as if freshly tilled, and the scent of living earth, that distinct, cool, damp fragrance farmers know as the smell of healthy soil, drifts across the garden. That white powder is sugar yeast. It costs less than $2 a packet. Yet it just accomplished what tens of millions of dollars in chemical fertilizers cannot. It called life back from the depths of the earth. You might think this is an old wives' tale, mere superstition, or completely baseless. But I am going to show you exactly why it works, the biological mechanics behind it, and why this knowledge has been deliberately buried for over half a century. It is not because it doesn't work. It is precisely because it works too well, and it is free. The real question is not whether sugar yeast can summon earthworms. The real question is, who has profited from keeping you in the dark? There is an industry worth $200 billion that depends entirely on one thing: that you never look down at your soil and think it can heal itself. The global fertilizer market, valued at exactly $197.6 billion in 2022, according to Grandview Research, is projected to reach $306 billion by 2030. That is not a market built on helping farmers. That is a market built on dependency. And the moment you understand what a $2 packet of yeast can do to your soil ecosystem, you begin to understand why that dependency was engineered so carefully and so quietly. Let's name the architecture of this system clearly. After World War II, the same chemical plants that produced nitrogen-based explosives needed a new market. The solution was synthetic fertilizer. By the 1960s, the Green Revolution, funded heavily by the Rockefeller Foundation and later institutionalized through CGIAR, the Consultative Group on International Agricultural Research, had successfully reframed farming as an industrial input-output operation. Soil was no longer a living ecosystem. It was a substrate, a medium, a thing you poured chemicals into to extract yield from. The $200 billion industry was born, and the ancient knowledge of soil biology was quietly pushed off every university curriculum that received corporate agricultural funding. Here is what that means in practical terms. A single 50-pound bag of synthetic NPK fertilizer, nitrogen, phosphorus, potassium, costs between $60 and $90 at any agricultural supply store in the United States today. The same nutrients, delivered biologically through an active earthworm population, stimulated by fermentation, cost you less than $2 in yeast and a handful of straw you already have. That is a 97% cost reduction. And that number does not even account for the compounding benefit. Because unlike synthetic fertilizer, which depletes soil biology with every application and forces you to buy more next season, earthworms reproduce, multiply, and do the work for free, indefinitely. The industry knows this. In 2011, the USDA's Natural Resources Conservation Service published a technical document explicitly stating that earthworm populations are among the most reliable indicators of long-term soil productivity, and that soils with high earthworm density require significantly less external nutrient input. That document exists. It is public. It has been public for over a decade, and yet it never became a headline, never became a policy, and never threatened the $200 billion market even slightly, because no one was paid to make it loud. This is not a conspiracy theory. This is market logic. When the solution to a problem costs $2, there is no profit motive to teach it. When the solution costs $80 per bag, every agronomist, every extension officer, every government subsidy program has a structural reason to recommend it instead. The $200 billion industry does not need to silence anyone. It simply needs to keep being the loudest voice in the room, and it has had 70 years of practice doing exactly that. But here is what they could not erase. They could not erase history. And the history of what yeast does to living soil is older than any corporation on Earth. In 1881, a 72-year-old man published what he believed would be his least important book. He had already changed the world twice, first with On the Origin of Species in 1859, then with The Descent of Man in 1871. But this final book, titled The Formation of Vegetable Mold Through the Action of Worms, was the one he had been quietly researching for over 40 years. Charles Darwin spent 4 decades studying earthworms in his garden at Down House in Kent, England. He measured how fast they pulled leaves underground, how deeply they aerated soil, how completely they transformed dead organic matter into living fertility. His conclusion, published just months before his death, was unambiguous. Earthworms are the most important animals in the history of agriculture. Not cattle, not horses, earthworms. Darwin calculated that a single acre of English garden soil contained an average of 53,000 earthworms, and that those worms turned over approximately 10 tons of soil per year per acre. The scientific establishment of his era largely ignored the finding. It was, after all, just worms, unglamorous, unpatentable, unprofitable. What the scientific establishment ignored, however, traditional farmers across Asia had already been practicing for centuries. In China, written agricultural records dating back to the Han Dynasty, roughly 200 BCE to 200 CE, describe methods of composting and soil fermentation designed specifically to attract and retain earthworm populations. Japanese farmers of the Edo period, between 1603 and 1868, developed a practice called bokashi, a fermentation-based soil amendment using rice bran, water, and naturally occurring yeasts, applied directly to field soil before planting. Korean natural farming traditions, formalized in the 20th century by Han Kyu Cho, and later documented by the University of Hawaii's C. Tahar Division, the College of Tropical Agriculture and Human Resources, recorded specific fermentation protocols that mirror almost exactly what modern soil biologists now understand about microbial signaling in rhizosphere environments. These were not guesses. These were millennia of careful observation encoded into agricultural practice. And they worked, not because ancient farmers understood the biochemistry, but because they trusted the result they could see with their own eyes, season after season, generation after generation. Then the 20th century arrived. The Green Revolution of the 1960s and 70s, backed by over $350 million in Rockefeller and Ford Foundation funding, according to historical records held by the Rockefeller Archive Center, systematically replaced indigenous soil knowledge with input-dependent monoculture farming. Extension programs trained a new generation of farmers to measure success in yield per acre, not in soil biology. The word fertility was quietly redefined, from a living, self-sustaining biological condition to a number on a bag of synthetic NPK. In one generation, 40 centuries of fermentation-based soil wisdom was reclassified as folklore, and the $200 billion market quietly took its place. But the knowledge never actually died. It survived in the hands of people who kept farming the old way, in rural communities that never fully trusted the new system, and in a handful of researchers working outside the industrial funding stream. And what those researchers found when they finally ran the controlled studies is the part that should make every farmer, every gardener, every person who grows a single tomato plant in a pot on their balcony stop everything and pay attention. The science is not mysterious. It is actually elegant. And once you understand the mechanism, you cannot unsee it. Everything begins not with the earthworm, but with what happens in the soil the moment fermentation starts. When you dissolve active dry yeast into water and apply it to soil covered with organic mulch, straw, rice husks, dried leaves, any carbon-rich surface material, you are not simply adding a nutrient. You are initiating a biological cascade. Yeast, classified under the species Saccharomyces cerevisiae, is a living microorganism. The moment it contacts moisture and organic carbon in the soil environment, it begins metabolizing, consuming simple sugars, producing carbon dioxide, ethanol, and a range of organic acids, including acetic acid and lactic acid, as metabolic byproducts. This process, aerobic and anaerobic fermentation occurring simultaneously in the micropockets of soil structure, does something that no synthetic fertilizer can replicate. It dramatically and rapidly shifts the microbial population of the soil. A 2016 study published in the journal Applied Soil Ecology, conducted by researchers at Wageningen University in the Netherlands, one of the world's leading agricultural research institutions, demonstrated that sudden increases in soil microbial biomass, particularly fungal and bacterial populations, triggered by fermentable carbon inputs, produced measurable increases in earthworm surface activity within 24 to 72 hours of application. The mechanism is chemical signaling. Earthworms navigate their environment almost entirely through chemoreception. They detect chemical gradients in soil water with extraordinary sensitivity. The organic acids and microbial volatile compounds produced during fermentation function as what soil ecologists call foraging attractants, essentially a dinner bell broadcast through the liquid film that coats every soil particle. The USDA Agricultural Research Service, in a 2019 technical report on soil health indicators, confirmed that earthworm populations respond to microbial biomass concentrations and that soils with actively fermenting organic matter consistently show higher earthworm density than adjacent control plots. The FAO, the Food and Agriculture Organization of the United Nations, in its 2021 publication, State of Knowledge of Soil Biodiversity, explicitly identified microbial activity as the primary driver of earthworm habitat selection, stating that soil carbon and microbial biomass are the two strongest predictors of earthworm abundance across all global soil types studied. This is not fringe science. This is published, peer-reviewed, institutionally verified research. The FAO is not a radical organization. Wageningen University is not an underground laboratory. These are the most credible agricultural research institutions on the planet, and they are all pointing at the same mechanism. Fermentation feeds microbes. Microbes signal earthworms. Earthworms transform soil. What makes the yeast application specifically powerful is the speed of the reaction. Synthetic fertilizer applied to biologically depleted soil that has been repeatedly treated with herbicides and pesticides, which the USDA's 2018 Soil Health Survey found affects over 70% of conventionally farmed American cropland, produces a chemical nutrient spike that plant roots can absorb, but it does nothing to the biological infrastructure of the soil. The earthworm population in heavily chemically treated soil can drop by as much as 90%, according to a landmark 1992 study by Dr. John Boland published in Ecological Applications. 90%. And without earthworms, you lose the biological tillage, the nitrogen cycling, the water infiltration improvement, and the humus formation that no bag of synthetic fertilizer can replicate at any price. $2 of yeast begins reversing that collapse within a single day. And what happens once the earthworms arrive is where the numbers become almost difficult to believe. A single earthworm is, by any measure, one of the most productive organisms on the planet relative to its size. Darwin estimated the numbers in 1881, and modern soil science has spent 140 years confirming and expanding what he found. A healthy population of earthworms in 1 acre of soil, the kind of population that a consistent fermentation-based soil treatment can establish and maintain, processes between 10 and 20 metric tons of soil per year. They do not simply move through it, they consume it, digest it, and excrete it transformed. Earthworm castings, the technical term for their excrement, contain available nitrogen at levels 5 times higher than the surrounding soil, available phosphorus at levels 7 times higher, and available potassium at levels 11 times higher, according to measurements published by Dr. Elaine Ingham, formerly of Oregon State University, and the founding director of the Soil Food Web Institute, whose research has been cited in USDA soil health training materials since 2008. Let that land for a moment. 11 times more available potassium, 7 times more phosphorus, 5 times more nitrogen. These are not marginal improvements. These are the exact nutrients that an $80 bag of synthetic NPK fertilizer is trying to deliver. And earthworm castings deliver them in a bioavailable form that plant roots can absorb directly, without the chemical processing that synthetic fertilizer requires, and without the soil acidification that long-term synthetic use inevitably produces. A 2020 meta-analysis published in the journal Soil Biology and Biochemistry, reviewing 57 independent studies across 25 countries, found that soils with high earthworm activity showed an average crop yield increase of 25% compared to earthworm-depleted soils receiving equivalent synthetic fertilizer inputs. 25% more yield from worms. That cost you nothing beyond the $2 you spent on yeast to invite them back. Now, here is the moment in this story where I have to be honest with you, because credibility matters more than drama. This method has real limitations, and you deserve to know them before you go any further. Fermentation-based earthworm attraction works most effectively in soils that retain at least some baseline moisture. Below 20% soil moisture content, the microbial cascade is significantly slowed. It is also substantially less effective in soils that have been heavily treated with synthetic pesticides, particularly organophosphates and neonicotinoids, which research published in the journal Chemosphere in 2017 found can reduce earthworm survival rates by up to 60% even at label-recommended application rates. If your soil has been in conventional chemical production for more than a decade, this method alone will not be sufficient. You will need to address the chemical load first, and in extremely sandy or extremely clay-heavy soils with poor organic matter content, the yeast application needs to be combined with a surface mulch layer to retain the moisture and carbon that the fermentation process requires. These are not reasons to abandon the method. They are reasons to understand it accurately. Because when the conditions are right, and for the majority of home gardens, backyard plots, and small-scale growing spaces they are, what you are about to do in your own soil is not gardening. It is ecological restoration. And that distinction matters because it means you are not just a person with a garden anymore. You are someone who is rebuilding a living system that took millions of years to evolve, that industrial agriculture spent 70 years dismantling, and that you are reclaiming with $2 and a handful of straw. That is not a small thing. That is an act of biological resistance, and now I'm going to show you exactly how to do it. The process is simpler than you have been led to believe. And that simplicity is itself a form of subversion. You do not need a laboratory. You do not need a certification. You do not need to buy anything from a company that has a stake in keeping you dependent. Everything you need either costs almost nothing or is already lying in your yard right now. Start with your yeast. You want active, dry yeast, the same kind sold in every grocery store, every market, every small shop in every country on Earth. The specific species is Saccharomyces cerevisiae, and the commercial product you are looking for is sometimes labeled as baker's yeast or instant dry yeast. Do not use brewer's yeast or nutritional yeast. Those are deactivated and will not initiate the fermentation cascade you need. One standard 7-gram packet, which costs between $0.50 and $2 USD depending on your location, is sufficient for approximately 10 square meters of soil surface. If you are treating a larger area, scaled proportionally, this is not a precise pharmaceutical process, and the biology is forgiving within a reasonable range. Your mixing ratio is 1 packet of active dry yeast dissolved into 10 liters of non-chlorinated water. This is the detail most people miss, and it is critical. Municipal tap water in most cities contains between 0.2 and 1.0 milligrams per liter of residual chlorine, which is enough to significantly inhibit yeast activation and kill a portion of the microbial population you're trying to cultivate. If you only have tap water available, fill your container the night before and leave it uncovered. Chlorine is volatile and will off-gas within 8 to 12 hours at room temperature, a process confirmed by the U.S. Environmental Protection Agency's drinking water technical guidance documents. Rainwater, well water, or river water are all preferable if accessible. Add 1 tablespoon of sugar or molasses to the water before dissolving the yeast. The sugar serves as an immediate energy source that activates the yeast cells rapidly, producing the fermentation reaction within minutes rather than hours. Molasses is preferable over refined white sugar because it contains trace minerals, particularly iron, calcium, and magnesium, that support broader microbial activity beyond just the yeast population. Unsulfured blackstrap molasses, available in most health food stores for approximately $4 to $6 per bottle that will last you many applications, is the optimal choice. But plain white sugar works. Do not let the perfect be the enemy of the functional. Allow the mixture to sit uncovered for 20 to 30 minutes after mixing. You will see it become slightly foamy as the yeast activates. This is your confirmation that the culture is alive and the fermentation process has begun. If you see no activity after 30 minutes, your yeast may be expired or your water too cold. Yeast activates optimally between 20 and 35 degrees Celsius. Below 15 degrees, activation slows dramatically. This is why timing your application to late spring or early autumn, when soil temperatures are in the optimal range, produces the strongest earthworm response. Before you apply, prepare your soil surface. This is not optional. The surface mulch layer is what retains the moisture that allows the fermentation to persist long enough for the chemical signals to travel through the soil water and reach earthworm populations that may be resting 30 to 60 centimeters below the surface. Lay a 5 to 10 centimeter layer of rice straw, wheat straw, dried grass clippings, shredded leaves, or any available carbon-rich organic material across the area you intend to treat. Wet this mulch layer lightly with plain water before applying your yeast mixture. Pre-moistening allows the yeast solution to penetrate downward into the soil rather than being absorbed and trapped in the dry surface mulch. Apply your yeast solution slowly and evenly across the mulch surface using a watering can or low-pressure sprayer. Do not use a high-pressure hose. You want the liquid to infiltrate downward, not run off laterally. Apply in the early morning or evening, never in direct midday sun, because UV radiation will degrade the live yeast cells before they reach the soil. Once applied, do not disturb the soil surface for at least 48 hours. The fermentation process needs time to establish, the microbial population needs time to respond and multiply, and the chemical signal gradient needs time to diffuse through the soil-water column to where the earthworms are resting. Within 24 to 72 hours, depending on your soil type, moisture level, existing earthworm population, and ambient temperature, you will begin to see evidence of activity. The surface mulch will show small disturbance points where earthworms have pushed through from below. If you gently lift a corner of the mulch layer without disturbing the soil, you will find earthworms, sometimes dozens of them, congregating in the moist fermentation zone immediately beneath. In soils that retain a baseline earthworm population, results are often visible within the first night. In more depleted soils, the initial response may be slower, but repeat applications every 2 to 3 weeks through a growing season will progressively rebuild the population. You are not waiting for a product to work. You are waiting for an ecosystem to wake up. And once it does not need you to maintain it. It maintains itself. This method is not magic, and pretending otherwise would make everything said before it meaningless. There are conditions under which fermentation-based earthworm attraction produces limited results, and you need to know them with the same clarity as you know the benefits. If your soil has been under continuous synthetic pesticide application for more than 10 consecutive years, particularly with organophosphate compounds like chlorpyrifos, which the EPA finally moved to ban residential use of in 2021 after decades of documented ecological damage, your earthworm population may be so severely depleted that the chemical signal has no one left to receive it. A 2017 study in Chemosphere measuring earthworm mortality across 18 pesticide compounds found that residual soil contamination alone, independent of fresh applications, reduced earthworm survival by 40 to 60%. In these soils, fermentation is a first step, not a complete solution. You will need to stop the chemical inputs, allow the residue to break down, which takes between 1 and 3 years depending on compound and rainfall, and apply the yeast treatment as part of a longer restoration sequence. Similarly, if your soil has zero organic matter content, compacted urban fill, construction rubble, pure sand, the fermentation cascade has no structural matrix to work within. Add compost first. Build the foundation before you call the inhabitants. But here is the truth that matters most. For the overwhelming majority of degraded home garden soils, backyard plots, and small farm parcels that have not been under heavy industrial chemical use, this method works, and it works faster than anything you can buy at 3 times the price. The limitation is real but narrow. The application is broad. And what comes next in this series of video will take everything you just learned one level deeper into territory that even most organic farmers have never explored. If you made it to this point, you already understand something that the $200 billion fertilizer industry spends enormous resources making sure the average person never connects, that the most powerful agricultural technology on Earth is alive, it is already in your soil, and it costs less than a cup of coffee to activate. That knowledge is not neutral. Knowing it changes what you do next, and what you do next changes your land, your food, your independence. So when I ask you to subscribe to this channel, I am not asking you to support a content creator. I am asking you to refuse to be the last person in your community who knows this. Every person who shares this video is putting this information in front of someone who may be one growing season away from giving up on their land entirely. Someone who was told by every official channel that the only answer costs $80 a bag and comes with a corporate logo on the side. You sharing this is an act of information resistance. It costs you nothing. It costs them everything if you do not. Leave a comment telling me what your soil looks like right now. Depleted, clay-heavy, sandy, recovering. Because the next video in this series is going to go somewhere that will make today's video look like the introduction it actually was. We are going to talk about a liquid that rice farmers in Korea and Japan have been fermenting for over 300 years. That contains a specific class of bacteria, photosynthetic bacteria, PSB, currently being studied in closed laboratory programs by 3 of the largest agricultural corporations on Earth, precisely because it can do to nitrogen fixation what today's method does to earthworm populations. They are studying it because they are afraid of it. You should know about it for exactly the same reason.